Now let's look at this numerical associated with the graduation test. So we all know that graduation tests are primarily performed because the crude rates are graduated using various mechanisms, either a graphical mechanism or probably by reference to a standard table or by using some kind of a parametric formula fitting approach. By doing an observation of the crude rates, they are smoothened to get a graduated rate, but again that smoothened rates, to check out their appropriateness to the reality or to the actuals, we perform graduation tests. So what we could see here is he wishes to test whether the underlying mortality from tuberculosis in the town is same as the national force of mortality. So it is being compared with respect to the national force of mortality. So this is what is the comparison we are trying to look at. So we got different age groups right from 5 years up to 84 years. Various age groups are present, and the number of actual deaths that have occurred based on the observations, and we also have data relating to the central exposed to risk along with the national force of mortality related statistics with us. Now, I am more interested in looking out the overall test of null hypothesis that the underlying mortality from tuberculosis is same from this town. So here the comparison is town versus national average, national force of mortality. Town versus national force of mortality is what is our observation. So that is where we are looking at an overall test. If I am looking at an overall test, I am more interested in a chi-square statistic, wherein my intention is I am looking at the force of mortality for this specific group. I want to compare the force of mortality with the national average using this particular central exposed to risk. So that is where I am defining the chi-square statistic. Chi-square statistic is what I am looking at. So we know the relationship between a z statistic and a chi-square statistic. The z is working out as the actual value minus the observed, minus the expected value divided by the square root of the expected. So because we are using a central exposed to risk and force of mortality, I will take based on the actual number of deaths minus the expected number of deaths. Here come to me using the central force of mortality, central exposed to risk, multiplied by the mortality of the sample, and I also take this value also has the central exposed to risk multiplied by the mortality of the standard table. So this is what is giving me the Zx. So if Zx is following a normal distribution, we know that over all the x's, the Zx square will follow a chi-square distribution with the number of age groups m degrees of freedom. So I have to use that kind of a mechanism and compute the chi-square test statistic here. Alright, for that let me just note down the numbers so that we can perform. So I have expected deaths in this category, or probably deaths in sample. So we'll call them as observed deaths. Those are the deaths in sample, observed deaths. Then we have central exposed to risk. Right, we have central exposed to risk, and of course we also have national force of mortality. We have a few numbers for each of them as a part of this calculation. We are looking at age groups 5 to 14. Probably I'll call them as 5 to 14. 15 to 24, something like that. 15 to 24, 25 to 34, 35 to 44, 45 to 54, 55 to 64, 65 to 74, and 75 to 84. These are the different groups we have. Then the observed number of deaths: 13, 47, 52, 50, 13, 47, 52, 50, 33, 23, 13, 3. Very good. There's a pattern. 33, 23, 13, and then 3. And when I'm looking at the central exposed to is 36852540, 36852540, 1938, 1687, 1938, 1687, 1386, 1018, 1386, 1018. Then I have 663 and 260. These are the central exposed stories. Now when I look at the national force of mortality, 0.0051, 0.0199, 0309, 0309, 0316, 0286, okay, 0230, then I have 0202, and then finally 0070. Okay, fair enough. This is what are the national force of mortality. So based on this, I can find out first of all the expected deaths. Basically, talking about if I am going with the national force of mortality to be applicable for this particular town also, then I am expecting the number of deaths as this number multiplied by the national force of mortality. So I am expecting 18.79 deaths in the age group of 5 to 14, and these are the numbers in the different age groups. So based on this, I can compute the value of ZX, which we have seen as actual observed kind of deaths minus the expected kind of death. I divide the same by the square root of the expected number of deaths, right? Observed minus the expected divided by the square root of expected, giving me the ZX. So working out to minus 1.3364, the same logic I can very well operate out extraordinarily. Then similarly I can talk about ZX squared, which is nothing but the squaring of each of these. So in each of them, this is working out to ZX squared. This is the value, the summation of all these ZX square is what will be my chi-squared value. So I'll call it a chi-squared value coming out as the summation of all these values. So my chi-square is working out to 5.17 as a part of the test statistic. So the test statistic chi-square is equal to working out to 5.174. I have to compare this value with respect to the critical value that comes out from the chi-square distribution, 8 degrees of freedom and 5% significance level. So the critical value for me comes out as a reference to the chi-square table, right? A reference to chi-square table. So I'll take that number here, 5 degrees, 5% significance level and 8 degrees of freedom. Sorry, I need to take it as the 95%. 95% confidence level with a 5% with a 8 degrees of freedom is working out to a critical value of around 15.5. Our calculated value is lesser than the critical value, so we do not reject the null hypothesis. When I say do not reject the null hypothesis, I cannot bring out any difference. So I cannot bring out any significant difference in the mortality rates. So probably it's like I cannot conclude any significant difference in the mortality rates between the town and the national average, town and the national values. So when I'm going with the overall chi-square test mechanism, I'm not able to reject the null hypothesis that the mortality rate regarding the tuberculosis in the particular town is anywhere significantly different compared to that of the national numbers. So that is one of the simple thing that is coming out for us as a part of the chi-square test. So wherever we are looking at the significance levels are much lesser. Probably one more way I can look at is because the expected value for each group as a part of the typical chi-square test rule, the expected value for each group should be having a minimum of 5 elements. And because it should have a minimum expected value of 5, if it is not, it is advisable to group the numbers. So in case I'm going ahead with respect to the grouping, probably it's as good as saying I'll group these two things, saying this is now I'll club 13 and 3 and I'll make it 16. The central exposed to risk also I'll club both of them, make it 923. So I can even go ahead with such kind of stuff and then work it out. Even then the chi-square is much lesser than the critical value itself. So either I do it for each by clubbing the groups, or I do it this way because there is only one group that is having an exceptional value. Whatever it is, these two are not very close by, so our decision will not change that drastically. So when we are performing the overall chi-square test, that is what is the conclusion that is coming out. There is not much of a significant difference between the graduated rates that are regarding the mortality rates which were graduated for the particular town when compared with the national mortality related statistics. Then we are talking of identify the two differences between the experience of the sample and the national experience when which the test you performed in one might not detect. So some of the tests which are really looked at when we really feel that chi-square test will not be sufficient enough, because chi-square test, as we have looked at when we discussed about the conceptual aspects, chi-square test is an overall test, but it does not look at the pattern over the ages, or some small differences are getting carried over. See, the chi-square is looking at the summation of many small differences. If there is one large difference, it reflects very sharply in the chi-square, but if there are many small differences, the chi-square may not observe them properly. So from that standpoint, we have various other tests to focus on. So one of them being the science test. So again, when I'm going with the science test, I'm primarily looking at the number of positive signs. The number of positive signs in terms of the deviation, and I expect that the number of positive signs is binomially distributed with the probability for probability of getting a positive sign being equal to zero point 0.5. So number of age groups and probability of getting zero point 0.5. So now let's see how many positive signs we had in the whole thing. Only one positive sign. So I am looking at, I will try to compute what is the probability of getting with this kind of a distribution, what is the probability of getting less than or equal to one positive sign. Because we got only one positive sign here, I am interested in finding out what is the probability of getting less than or equal to one positive sign. So probability of getting zero positive signs is going as 8C0 multiplied by zero point 0.5 to the power 7 and multiplied by zero point 0.5 to the power 8. So probably I can directly take this as zero point 0.5 to the power 8. So saying the probability of getting 0 positives is that much, and probability of getting 1 positive is going to be this much. So probably a probability of getting one or less probability of getting one or less positive sign is coming out only to 0.035, which is working out to around 3.5%, only 3.52%. The probability of getting one or lesser positive sign is only around 3.52%. So because I am going with this 3.52%, I am comparing this with a 2.5%, which is a 5% level of significance in one tail. So I am looking at I'm comparing it with 2.5% because 3.52 is greater than 2.5. I cannot reject the null hypothesis. So again, even using the science test, I am making I cannot differentiate that the particular sample which I have used is anywhere significantly different from the national average. This particular town's mortality statistics is more or less same as that of the national statistics as well, because I am not able to differentiate it even using the science test also. The same way we can use another mechanism, which is cumulative deviations test. What are we doing in this cumulative deviations? I am only looking at the deviation in each of the groups. Right? I am looking at the actual minus the expected. So I am looking at the deviates are probably, it's as good as saying when I am looking at the total observed deaths. Probably when I am going with the cumulative deviations test, I am looking at overall. So I am looking at total observed deaths minus total expected deaths divided by square root of total expected deaths. I assume that this follows a kind of a standard normal distribution. That is what a cumulative deviations test works out. So here I can find out what are the total number of observed deaths. I am saying total observed deaths are 234, whereas using this table, the total national statistics, the total expected deaths are 260. So working out for our Z value in this process, coming out to total observed minus the total expected divided by the square root of the total expected, which is working out to minus 1.65. Right, it is working out to minus 1.65. So if this is following a normal distribution, again I am going with this particular aspect. When I am looking at it as a normal distribution, I am comparing it with 95% confidence level working out to 1.96. So what I could see is minus 1.65 lies between minus 1.96 to plus 1.96. So even in this case, the conclusion is coming out that do not reject the null hypothesis. Means again, even the cumulative deviations test is giving me the similar kind of a conclusion that there is not much of a difference between this particular town's mortality rate based on tuberculosis versus the national mortality rate. So even this is giving us a similar kind of an understanding. Probably if required, I can very well look at individual standardized deviations test, because we have already computed the Z statistics here. All I want is the Z See, if I'm assuming that each of these groups is following a kind of a normal distribution, we should not see even a single value lying, we should not see any z value lying outside the plus or minus 3 interval. Yes, that is happening. More or less, we should see not more than one deviation in the plus or minus 1.96 interval. Even I could not see even a single one. So under all these things, again this is coming out that there is not much of a significant difference. This particular individualized standard deviations are very much adhering to the normal distribution. So again, I don't have any sufficient evidence to reject the null hypothesis. So even using the individual standardized deviations test, I am not able to reject the null hypothesis significantly. So here what we could typically see is all these various tests that we have really performed. We can think of various others. I can think of using a grouping of signs test, or I could look at a serial correlation test, whatever we are looking at. Whether I have looked at it from an overall perspective using the chi-square test, or probably even when I look at it from an individualized perspectives using the science test or cumulative deviations or individual standardized deviations, the results are more or less similar. So from here I could very clearly say that the mortality, whatever that we are derived based on the tuberculosis specific to this town, is matching more or less with the national mortality related data. So that is how whenever we have tried working on any graduated model, we have to test it for significance by using these various statistical tests and then making conclusions accordingly. Alright. Now let's look at one interesting question as far as the statistical tests are concerned. Just look at it slightly different usage, not necessarily in the actuarial space, but this is more talking about the usage of the statistical tests even to test the uniformity across the climates of two different regions. Just look at this question. Rocky Bay is a small seaside town of north of Europe. The tourist office has claimed that in August, Rocky Bay has a Mediterranean climate. An actuarial student spent August 2009 on a holiday in Rocky Bay with his family. Returned home, he thought it might be interesting to examine the claim by applying some of the methods. For each of the 31 days in August 2009, he collected the data recorded by various meteorological officers on the maximum temperature in the Rocky Bay and the mean of the maximum temperatures reported in the same place of the Mediterranean region. On the same date in different places of the Mediterranean region, so he has found out positive means the Rocky Bay's temperatures are greater than the Mediterranean temperatures, and minus is indicating that the Rocky Bay temperatures are lesser than the Mediterranean temperatures. Now he is making trying to test the hypothesis where the null hypothesis got established that there is no difference, that there is no significant difference between the Rocky Bay's temperatures and the Mediterranean climate temperatures. Right? So from a temperature standpoint, the long run average temperature in Rocky Bay is more or less same as that of the Mediterranean climate. So that is what is the null hypothesis that got established, and obviously the alternate hypothesis goes the opposite of the same. So going ahead with testing for the same, we can very well test it using the science test. The signs are more or less random. So that is what I could do as a part of the science test. When the signs are coming out more or less random, then we can say there is not much of a difference between the two. But if the signs are following some kind of a pattern, then probably there is something either much better or much worse compared to the Mediterranean climate. So that is where we are looking at the number of days, the total number of days for which we have collected the data is 31. Okay, so let me see, the number of days for which we have collected the data is 31. Number of positives means on the number of days where the Mediterranean climate, where the Rocky Bay climate is having higher temperature than the Mediterranean is around 7, and the negatives are around 24. Now my intention is to really find out what is the probability that the number of positives, if at all, there is not much of a difference, what is the probability that the temperature that only on 7 or fewer days we see that the Rocky Base climate is more, and the remaining 24 days there is nothing much. So one, I can use either a binomial distribution for estimating the number of days for which the temperature in Rocky Bay is greater than that of the Mediterranean. I am primarily checking out what is the probability that the temperature in Rocky Bay is greater than that of the Mediterranean. So I can go with the binomial distribution kind of a mechanism, wherein I am simply looking at it as 31, 0.5. I am assuming that if at all there is some kind of a randomness, or there is not much of a pattern between the Rocky Bay temperature and the Mediterranean climate temperature, then there should be an equal chances of Rocky Bay exceeding the Mediterranean or Rocky Bay falling below the Mediterranean. That's the reason we are comparing it with a binomial distribution whose n is 31 and the p is 0.5. Either I can use a normal distribution approximation to it, because we have almost 31 days of data. So if I am using the normal distribution approximation, the same will work out as a normal distribution of NP, which is 31 times 0.5, 31 by 2, which is 15.5, and variance NP into 1 minus P. So 15.5 times 0.5, half of 15 and half, or 31 by 4, 31 by 4 giving me 7.75. So either I can look at it as a normal distribution with these two. So if I am going with that kind of a concept, I can very well compute the Z value. The Z value works out to X minus mu. X is the actual number of positives, 7 minus mu. X minus mu divided by square sigma, which is square root of 7.75. So my Z is working out to around minus 3.05, and if at all I want to look at it with respect to a normal distribution, see, one thing is the Z minus 3.05 is lesser than minus 1.96. So at 95% confidence interval, I can reject the null hypothesis and say that there is a significant difference between the Mediterranean climate and a Rocky Bay climate. The Mediterranean climate is having much higher temperatures, or Rocky Bay climate is having a much lesser temperature compared to a typical Mediterranean climate. I can do that using a normal distribution approximate, just like the way I have done now, or we can directly use a binomial distribution itself. I just want to know what is the probability that there are 0 positives, 1 positive, and like that, what is the probability of having 7 or below number of positive values going with this kind of a going, if at all it is uniform, if at all it has been uniform, or if at all there is no difference between a binomial, between a Mediterranean climate and a Rocky Bay climate, a binomial distribution up to 7 positives should give me a probability which is slightly higher than even 5%. So let me see binomial distribution here, n c 0 into, probably I can directly take it as 0.5 to the power 31. So if I am looking at 0 or below, the overall thing is working out to just 0.0016. If at all it has been not of a much of a difference, what we could see is the 7 or below number of positives, the probability of occurrence is just around 0.1%. This is again much lesser than at least 2.5%. So we can very safely conclude that the Rocky Bay climate is much lesser, significantly lesser compared to that of the Mediterranean climate using this science test mechanism. But what we are typically interested in trying to understand, especially from this claim, why the test might not be an appropriate. Here, all these could be interdependent, because yesterday's temperature could very well influence the today's temperature. So, whatever was one day's value, it could influence the consecutive days very significantly in any location. So, the number of positives and number of negatives, they are not completely random, they are not completely independent. So, that's one of the prime reasons this test may be challenged quite comfortably, right? And the data which has been taken was only for 2009. It's not, but the assessment is primarily saying the long run temperatures, right? Because the claim is more of in general. Rocky Bay has a Mediterranean climate. This is more of a general kind of a value, whereas the data collection is more to 2009. So there is a kind of a data collection bias that is that has occurred, which could very well be challenged and which can threaten the goodness of the fitment. Apart from the statistical aspects of it, the data collection should have been more on a longer time frame rather than just restricting to August 2009. And it could very much happen that the temperatures in 2009 would have been slightly lesser in case of would have been slightly lesser in case of the Rocky Bay compared to the Mediterranean region, or probably the Mediterranean region would have been hotter during this time frame. And at what places, the locations where the data has been collected is very much important. And the claim was talking of a Mediterranean climate. It just need not be with respect to temperatures alone. It could be with respect to rainfall, it could be with respect to humidity, it could be with respect to various factors. So, only after all these various factors are considered, then only this kind of claim can quite comfortably be tested. So, that is where we have to really understand that whatever the data that has been collected, or whatever the tests that have been performed, may lead to be a relook to come out with much and much better stake of the claim, or much and much better questioning of the claim. But from our perspective, as far as the usage of the statistical technique is concerned, in this case, because of the negatives and positives that are being mentioned, we can very well look at the usage of the science test, and we can use it from an interpretation standpoint. All right. Now we will look at the different tests of graduation, a numerical example relating to different tests of graduation, and primarily the different mechanisms that have been engaged with respect to smoothening out the crude rates to graduated rates, and typically trying to understand which of the tests are talking about the goodness of fitment, and which of them are not looking at the goodness of fitment of the data. So from that perspective, we are looking at this example. A life insurance company, it has priced its whole life contract 30 years back, and they have used a standard mortality table for that. Now their point of view is to see whether that kind of a mechanism that was used almost 30 years back, is it still reflecting the current mortality experience. So for that, they have looked at their data for the people who are aged between 50 to 59 years. How many of the policies are there? How many of them are exposed to risk during 2009, and out of them, how many are dead during this period? And when they are looking at the standard table for each of the ages, this talks about the number of survivors. So from here, I should be able to find out my probability of survival as well as the probability of death. Px talking about the probability of survival, and Qx talking of probability of death during that particular period. Using that, I can find out the expected number of deaths, and from where I can find out compare it with the actual number of deaths which are registered here, to see whether the model is still a good fitment at this particular point in time. So let's take the scenario into the spreadsheet. Age, last birthday. So age, last birthday is something which I am taking, and I have the values directly from 50, 51 up to 59. So the people whose ages are between 50 to 59 are being monitored. Okay, exposed to risk. So I'm looking at the exposed to risk during a particular period. These are the numbers: 2381, all right, 3177, 3460, 1955, 3122. These are the numbers. I'm just entering the numbers, and then we'll discuss the things of. Okay, these are the exposed to risk during that particular period, and I'm talking about deaths during that period: 16, 21, 22, 15. Okay, 24, 29, 26. Oh, sorry. Okay, 24, 29, 26, 31, 39, 48, 31, 39, and then 48. These are the number of deaths. Okay, from the standard table, the number of survivors, right? Number of survivors up to 50 years. I am looking at number of survivors up to 50 years: 32,669. 32,513 here, 32,338, 32,143, 31,926, 31,685, 31,417, 31,120, 30,795, 30,435, and 30,039. Now from here I can find out the probability of survival px. Probably see, these are the number of people who have survived until 32 until 50 years. These are the people who have survived until 51 years. So we can talk about the probability of a person who is currently aged 50 surviving for one more year, which is typically coming out or being represented as px, p50. So I can talk about the P50 in this case is L51, number of survivors until 51 divided by number of survivors until 50. So the PX is coming out to this particular number, and from here I can find out the PX for all these particular age groups. And from here I can very well find out the probability that a person age 50 is going to die within the next 1 year. That is the QX, which is coming out as 1 minus px, working out with this kind of numbers. So these are my qx's when I go with that particular standard table. These are my qx's, and now that I have this being the exposed to risk, I can find out the expected deaths. The expected deaths as given by that standard table for each of the years, I can multiply whatever is the exposed to risk during that period. I multiply it with QX for that period, saying 11.36 were the expected deaths during that period, whereas the actual deaths were 16. The same logic I can continue. So for each of the years here, we are expecting a deaths of 51, whereas the actual deaths were 48, and so on. So we have the observed deaths, actual deaths, we have the expected deaths. So from here I can find out O minus E, which is the observed deaths minus the expected deaths. I can very well find out. Okay, observed deaths minus the expected deaths coming out to this much. So basically it's like at least for the first few years I'm seeing that the observed were much higher than expected, right? So the expected number of deaths were much lesser, whereas the actual deaths that occurred were much higher for age groups of 50 to 54. But after that we are seeing that the actual number of deaths were much lesser than the expected number of deaths. So based on this, we can actually get into the computation of a chi-square value, so that we can do a chi-square test. So for doing the chi-square, I require observed minus expected whole square divided by expected. That is what goes as a part of the chi-square determination. So for each of them, I take observed minus expected whole square and divide it by the expected. With this kind of values, I can find out the chi-square. The chi-square is nothing but the summation of those particular values. The chi-square for me comes out to the summation of these values, which is coming out to somewhere around 3.835. Right, that is coming out to be the chi-square value. And once I have this particular chi-square, I can start getting into a testing process. What is the testing process here? What is the null hypothesis as a part of the testing? The null hypothesis for me is very clear. The null hypothesis for me in this case is pretty clear, saying whatever the observed data which I looked at is more or less reflecting, the observed data is more or less reflecting the data which is coming from the standard table. So the mortality rate that is coming from the observed observations is more or less a representation from the standard table itself. That is what is the null hypothesis, and the alternate is saying there is a huge difference between, there is a significant difference between the observed mortality rates, and the rates coming from the standard table. Means the standard table is nowhere a perfect, a decent reflection of the actual mortality rates that are coming up now. So I can very well do that testing using a chi-square test. And of course, because we have 10 different age groups, we did not use any kind of a parameter, or we did not have any kind of a choice of table. So because of all these things, no degrees of freedom is lost. We have observed earlier that if I have to find out the degrees of freedom for this chi-square test, I start with the number of age groups, and then try reducing it one for choice of table. I did not get into the choice of table here. We did not put any kind of parameters on the various, we did not determine any number of parameters or any formula for it, or even we didn't have any kind of constraints. So probably because of that, there is no loss in the degrees of freedom at all. So I can very well look at the typical critical value for this chi-square test. Let's say at 5 degrees of freedom, at 10 degrees of freedom, and at 5% level of significance. So probably I can very well look at the chi-square value at 5% level of significance and 10 degrees of freedom. The chi-square, I'm talking about on the higher side, so 95%. Okay, the chi-square value for 95% degrees of freedom, 95% confidence level, and 10 degrees of freedom is operating out to 18.3. My calculated value is much lesser than 18.3. So I cannot reject the null hypothesis. So fail to reject the null, which means I am going ahead with the null hypothesis, saying that there is not much of a significant difference between the actual observed values, observed mortality rates, and the rates that are coming from a standard table. However, we know that the chi-square test could give me only a broader picture, but it ignores a lot of smaller problems that can come out in the process. So I may think of doing different other kinds of tests to assess whether the null hypothesis can still be taken through, or it cannot be. So from that perspective, I can look at the various other tests also. Apart from the overall chi-square test, I can look at the different other kinds of possibilities. So I can look at, let's say, first a cumulative deviations test. Right, I can look at a cumulative deviations test to primarily look at the overall bias that is there in the process. Okay, I can find out the overall bias here. Right, I could very well look at the overall bias, which could give me the summation of just O minus E. The overall bias is coming out to somewhere around 1.61, whereas the overall expected number of deaths is coming out to somewhere around 269. So the test for cumulative deviations test, which is doing the overall bias, is I do the summation of the all the overall deviations, and I divide it by the square root of the expected number of deaths. So this is giving me a number 0.09, and again this number is also lying between minus 1.96 to plus 1.96. So again, so basically it's like at the overall level I'm trying to find out. So probably if you look at the overall actual number of deaths, it goes like this. The overall actual number of deaths is 271. Overall expected number of deaths is 261. So the cumulative deviations test is nothing but at an overall level I'm looking at the actual number of deaths. At an overall level I'm looking at the expected number of deaths and dividing it by the square root of the expected number of deaths. So this is what and this is being compared with respect to a normal distribution, standard normal distribution, mean 0 and variance 1. So because this value lies between minus 1.96 to plus 1.96, I cannot reject the null hypothesis. So I cannot reject the statement that there is a significant difference. I cannot make a statement as saying that there is a significant difference between the actual observed observations versus the standard table based numbers, or probably I don't have any strong evidence to conclude that the standard table which was designed 30 years back is not reflecting the current mortality experience. I cannot reject it on that grounds. And same way, if I'm trying to use, let's say, the another test wherein I'm looking at individual standardized deviations test. Individual standardized deviations test. Here we have a problem, because if we are typically looking at it, we expect that each of these individual deviations follow a standard normal distribution, mean 0, variance 1. Means we could see that in a group of 20, when I'm talking about a 95% confidence interval, we are talking about values lying between 1.96 minus 1.96 to plus 1.96. So only 5% of the observations should be outside this interval if it has to be normal. But what we are observing is 1, 2, 3, 4. 4 observations out of just 10. 40% of my observations are completely outside this range. Right? So typically we are looking at so many observations. Sorry, I'm talking about these. The not just observed minus expected. We are looking at observed minus expected, the square root of these numbers. So we are looking at the square root of this, or probably observed minus expected. If I have to look at it, this is nothing but the square root of this. I could see that hardly any one single value lies outside that plus or minus range, which means here also it is quite clearly evident that none of these values, or probably I can look at the observed minus expected divided by the square root of the expected. If I look at each one of them, so that I don't ignore the positive and the negative sign, it is quite clearly coming out that there is not even a single value that is lying outside the plus or minus 1.96 range. So even through this, I cannot reject the null hypothesis, and I am forced to go with the null hypothesis itself. There is not much of a difference between the actual observed rate and the ones that are determined by your standardized table. But however, if I am trying to run a couple of other tests, here one of the major things that I am observing is there is some kind of a pattern. At least between 50 to 54, we see that the difference between actual to expected is positive, and after that there is negative. So there is Not much of a randomness. It looks like some kind of a pattern, right? As the age is increasing, it looks as if the actual number of deaths vis-a-vis the predicted are decreasing. So some kind of a gradual drift is what we are observing from strongly positive to a strongly negative kind of numbers. So that's where sometimes we prefer doing something to do with either the science test or grouping of science tests, because here we have only one group, one change from positive to negative. Overall, if I am seeing, these five are positive, five are negative, but there is only one change from positive to negative. So here, if I talk about the number of deviations n, it is 10. Number of positive deviations n1, it is 5. Number of negative deviations n2 is 5. And probably I am talking about the number of groups which is working out to just 1. So based on this, if I want to find out what should be when I'm looking. So if at all there is only one change, what is that appropriate number for which I'm looking at? If at all there is only one change, what is the probability for that? I can look at the probability. If at all there is only one change, the probability of that occurrence is just n minus 1. I can use this formula, n minus 1 c n1 minus 1 c t minus 1 multiplied by n2 plus 1 ct, and I divide it by mc n1, a total nc n1. So this is what we can typically see. So probably if I am having only one, if I am having only one, the probability I can very well find out n1 minus 1 ct minus 1. So n1 minus 1 is 4, n1 minus 1 ct minus 1. So if I am talking of only one, I am talking of c0. I am multiplying this with n2 plus 1 ct. So n2 plus 1, I'm talking of 6, and ct, which is 1, and I'm dividing this entire thing by nc n1. So it is coming out as the combination of 10c5. Now this is giving me a probability of just around 2.3%, which is lesser than 5%. So in this case, I can reject the null hypothesis, and I can very clearly say that there has been some kind of either overgraduation or undergraduation with the ages. There is some. So, because of this, though the chi-squared could not identify any clear significant difference between the actual and the table, but the grouping of science test is able to reject the null hypothesis, saying that the graduated rates, the actual observations are not fitting properly with the graduated rate. So like this, we can very well go ahead doing the different kinds of tests. Probably just to understand, I can even get into either a science test, right? When we are going with a science test, instead of grouping of science, I can even look at a science test wherein again I am interested in looking at the overall bias in the pattern, wherein I am looking at it, if at all there is not much of a bias, it should follow a kind of a binomial distribution with n as 10 and p as 0.5. The number of positive signs are 5, so the probability of getting 5 positive signs is going as 10c5 into 1 by 2 to the power 5 into 1 by 2 to the power 5. This is the probability of getting for 5 positive signs. I could look at 5, 6, 7, 8, 9. So I can very well find out what is the probability. So probably let's put out 0, 1, 2 up to 10 if I'm looking at the probability. So I'm taking it as combination of 10 comma 0, 10C0 into zero point 0.5 to the power 10. So what is coming out is the probability of 5 or more positive signs is almost probability of 5 or more positive signs is working out to almost 62.3%. So anything is greater than 0.05, so I cannot reject the null hypothesis here, so I may have to go with the null hypothesis going with the science test also. But one more test which we can discuss in this case is the serial correlation test. I'm trying to do a correlation between the Z. I'm trying to do the correlation between these numbers, which are my Z, which have come out as, right, I'm trying to find out the correlations between these and probably with one period lag of these. I'll try to find out the correlation between them. So I could, let's say if I'm using the correlation between these and these with just one period lag, Zx and Zx minus 1, I'm trying to find out the correlation which is working out to somewhere around 0.88. The correlation is, that is what we are calling as the serial correlation. So I'm talking about the correlation that is coming out between these two sets of numbers as 0.88, and based on that I can even test out this particular correlation with a t-test, right? What are probably I can compare this particular correlation into, or I can find out a t-value corresponding to this serial correlation, or the other simple way, once I have got the correlation value, I can test out that particular correlation into R. I can find out a statistic which is R multiplied by square root of the number of observations, which is 9. R into square root of 9 is coming out to 2.66. I'm comparing it with respect to a normal distribution. So as long as again it is, if I'm looking at a 5% level of significance, it should be more than 1.96. If it is more than 1.96, I can reject the null hypothesis. So I am able to reject the null hypothesis here and making a statement that the table is not reflecting the actual experiences in a better way. So some of the tests are giving me a conclusion, especially when I'm looking at the serial correlation, the dependency of the past with for the future. There is a lot of serial correlation that is existing, which is providing me a strong evidence that as the ages are progressing, the mortality rates that are coming up are more or less dependent on the previous period. So the graduated rates which have come through our experience, they are not reflected properly through the standardized standard table that has been used. So these are the various tests of graduation that we can use to make a conclusion about whether the actual observed experiences are in line with the graduated with the experiences coming out of the graduated table or not. All right.